Right now, Earth is being constantly bombarded by energy from the sun, but we survive because of a giant magnetic shield called the magnetosphere. This is the solar wind, a continuous, fast-moving flow of tiny particles, specifically protons and electrons, streaming outward into deep space. But occasionally, that steady breeze becomes a sudden, violent burst of energy, a solar storm. These eruptions throw off so much material that they completely dwarf the everyday solar wind. When a storm of that magnitude hits, our protective shield actually stretches and buckles under the immense pressure. And when the barrier bends far enough, high-energy particles sneak inside. As those leaked particles dive toward the poles, they collide with and excite atoms high in our atmosphere. We see the visible result of those collisions as the glowing northern lights. These same particles penetrate the upper atmosphere, colliding with our technology. Crippling satellites in orbit, severing radio communications, and frying ground-based power grids. Our entire modern infrastructure sits totally exposed to the weather of deep space. Securing this infrastructure requires investment in two distinct directions: global monitoring and physical fortification. The first strategy is early warning. To predict space weather, we have to track the exact movements of our magnetic shield. That effort took a massive leap forward in May 2026 with the launch of the SMILE spacecraft. Look at this diagram of SMILE's flight path. It flies in a highly elliptical orbit, carrying it 121,000 kilometers away from Earth, about 1/3 of the way to the Moon. From that unique vantage point, it can stare at the entire magnetosphere for up to 40 hours at a time. Its primary mission is to map the magnetopause, the absolute outer edge of our shield. It uses a specialized lobster eye X-ray telescope to see exactly how and where that boundary moves during a solar storm. The spacecraft is packed with 4 distinct scientific instruments. Tools like a light ion analyzer and a magnetometer allow it to directly measure the speed, density, and magnetic strength of the incoming solar blast. Operating at this macro level requires serious financial commitment. Between development, launch, and a 3-year lifespan, the SMILE mission costs approximately $150 million. But the value of this surveillance is clear. By pinpointing exactly when and where the magnetic shield bends, we gain the crucial early warnings needed to safely power down grids and satellites before the brunt of the impact arrives. But what happens if the forecast is wrong, or the warning arrives too late? That question leads us to the micro-level defense, radiation hardening our electronics. To understand this, we have to look at the core threat to a microchip. It is called a single event upset. This occurs when one rogue solar particle carries enough high energy to strike the silicon and physically flip a bit of computer memory from a 0 to a 1. This diagram illustrates the first engineering countermeasure, design hardening. Engineers build triple redundant circuits that process the exact same data simultaneously. If one circuit is damaged by a strike, the 3 pathways hold a vote, and the logic gate ignores the anomaly. The second countermeasure is process hardening. Here, manufacturers change the physical material itself, using silicon on insulator wafers that add a thick barrier. This makes the chip naturally less sensitive to the radiation passing through it. The third and most brute force countermeasure is physical shielding. Engineers wrap the component in dense materials like ceramic or tungsten to absorb and block the particles before they ever reach the delicate chip inside. This demand for protection is fueling a specialized industry, with the market for radiation-hardened electronics projected to grow from under $2 billion today to $3.4 billion by 2035. The fundamental argument for this fortification approach is independence. A rad-hard chip provides immediate, permanent, built-in safety that works even when space weather warnings are missed. Focusing on only one of these paths leaves a critical opening. Forecasting without hardened hardware leaves our satellites defenseless if a sudden solar strike outpaces our warnings. Conversely, relying solely on physical fortification is expensive. A single radiation-hardened chip for a satellite can cost up to $100,000. Furthermore, ignoring the macro interactions between the Sun and Earth leaves us blind to the larger cosmic environment. The most practical solution is a balanced plan. Humanity must continue funding orbital missions like SMILE to maintain our global situational awareness. Concurrently, we must develop cheaper radiation-hardened components. With thousands of vulnerable small satellites launching in the coming decade, we need affordable ways to protect that orbital infrastructure. Mastering the environment of space requires both sight and armor. Combining these approaches provides the early warning needed to prepare for the storm and the built-in durability to survive it.